the limit state of serviceability with that of ultimate limit state. And in the last lecture we highlighted the importance of what we call as characteristic, maybe load, maybe strength of the material. As we agree strongly that both the environmental loads encountering the marine structures and the strength of material out of which these structures are constructed has lot of variabilities, and uncertainties in their computation as well as in their assessment of strength. Now, to account for this we introduce an adjective in terms of these estimates what we call as characteristic. Now, we agree that if the load and strength are to account for different variabilities or uncertainties which is inherently present in their estimates, then the value should have been probabilistic, it cannot be deterministic. So, to handle the probabilistic nature of these uncertainties we introduce a term called characteristic, and we agree that the distribution of these uncertainties or the variabilities based on which they vary normally get distributed, then we said that the distribution of their means I call this as load and this as response. So, the hatched portion what you see here is actually the probability of failure. Now, this becomes my mean of the load and this becomes my mean of the response. Now, I assume two distributions R1 and R2. So, R1 may not have any superposition or any overlap with that of the load, whereas the distribution R2 may have an overlap with the distribution of the load. So, we ensure that when the strength or the resistance is lower than that of the applied load, it indicates a failure phenomena here. Now, this can be equivalently understood as two distributions without overlap. I do not want a probability of failure, that is my ideal design. So, I select the mean in such a way that they do not have any overlap, agree, but the difficulty here is then how will you account for the excess in the load estimates or deficiency in the strength because of deterioration. So, we fix up what we call the percentile fractile values, we call this as SP and this point as let us say RP, and RP is gamma of SP. So, obviously you will see that SP and RP are essentially certain percentage of the fractile of the distribution. So, essentially SP is selected as 95% and RP is selected as 5%. So, what does it mean is whatever load you have assumed on the structure, the probability of exceedance of that load in the lifespan of the structure is only 5%, that is 95% it is reliable, and whatever strength you have appropriated in the design 95% that strength will be met, but there is a probability of exceedance of this or probability of loss of the strength only by 5%. So, what I am doing is instead of moving the mean value closer, I am keeping the mean value away, but I am fixing up two numbers which are called the characteristic values. So, these SPs and RP will define the characteristic nature of the load and strength respectively. Now, as I said, they are independently varying, because the load variation or the uncertainties associated with the load has no direct connectivity or dependency on the uncertainty or variabilities associated with the strength of the material. So, they are independently varying. The parameters on which load varies or uncertainties associated with load will be different from that of the varieties of parameters what you have for strength, but for our understanding in the design we have to look for the safety as an integral unit of load and strength. We are looking for the safety of the system, so we have to connect them. So, the connection is essentially by this equation, where gamma will give you the margin of safety. So, SP will be associated with 95% of the fractile, whereas RP will be associated with 5% of the fractile. This is of course with the load, this is of course with the strength. So, the probability of exceedance of the load in the lifespan of the structure is only 5%. Whereas the probability of deterioration of strength during the lifespan of the structure is only 5%. Is that clear? So, I am putting the same number, but the meaning of explanation is different. This is probability of exceedance, this is probability of deterioration, okay. That is probability of not meeting the strength is only 5%. Once we say that the load as well as the response are normally distributed, then once the load and the response are normally distributed, then the relationship between the fractile point which I call xp, the mean and the RMS, that is the root mean square, will be given by the following equation. Xp is mx plus or minus Kp of sigma x. I think this is equation number 2. Now, the fractile point can be selected in such a manner which depends on the value of Kp, okay, because the mean and standard deviation of the distribution, be it load, be it resistance, is known to us. So, to select a fractile percentile point, the whole equation now depends on the Kp value, okay. Various international codes advises you to select this value in different manner, okay. Let us look at what the Eurocode does. Before that, we will have a small table which plots the value or which gives the value of Kp and correspondingly the appropriate percentile of probability, okay. let us say the values of fractile points which I should say Kp, I should say table. I will give the percentage probability and the Kp values 20, 10, 5, 2.5, 2.275, 1.135, 0.0032. The values of Kp for different percentage are given here. 0.842, 1.282, 1.645, 1.96, 2, 2.326, 3 and 4. Now, for example, Eurocodes select Kp as 2, which implies that there is a chance of exceedance of the characteristic values. I am saying values, it may be load, it may be strength as well, in the service life of the structure only by 2.275%. Okay. So, what does it mean? Neither the load nor the strength will deteriorate less than about let us say 2.25%. So, the load whatever you have estimated will be as accurate as 100 minus 2.275. The strength will be available as close to 100 minus 2.275. So, directly the probability of exceedance of the load during the service life is only 2.275%. The probability of deterioration of the strength of the material during the service life is only 2.275%, the same meaning as we have here. Okay, that is for the Eurocode. So, different code define different standards of the Kp number, which is the value of the fractal points in the distribution, to explain the characteristic value of the load and strength. In Indian codes this number is 5%. Okay. So, the Kp is 1.645 for Indian codes. So, this can vary different codes etc. So, we are not debating on which code is following what number etc. The point is how accurate or how less accurate we are in allowing the load to exceed or to allowing the material to deteriorate. We say I will allow a 5% deviation during the service life. Eurocode says no, let us allow only 2.275. Remember very carefully, the lesser the percentage of allowance you are giving, or the higher the number of Kp you are using in your assumption, the accuracy of computing the load and strength is demanded. Okay? Because if you look at Kp4, it means it is only 0.0032 percentage. Practically load neither the strength should vary at all. Is it clear? So that is the meaning. So the probabilistic nature is indirectly brought in the design, in ultimate load design, by associating an adjective to the load and strength. Then these two are combined with a safety value which we call gamma. Okay. Now, so I should say the safety factor gamma is Rp by Sp, which I can write as characteristic strength by characteristic load. Now this safety factor is associated with two components. One is the material, other is of course with the load. So let us say for design purposes we can split gamma into two components, namely gamma m and gamma f. Gamma f relates to the load, and gamma m relates to the material. Some codes, for example Indian codes, call this, when this gamma f is multiplied to the working load, I call that as factored load. See, factor in term of mathematics is always a number less than 1, okay, but gamma f is always more than 1, right. So factored load does not mean you are decreasing the load, you are enhancing the load by some percentage which will account for uncertainties or variabilities. Okay. So I want to substitute this gamma as a product of gamma f and gamma m in equation 3. So substituting 4 in 3, I should say gamma f gamma m is Rp by Sp so I should say Sp into gamma f, because Sp is related to load, Rp is related to strength which is the material. I am grouping them, okay. This is the load, this is the material. So gamma f into Sp is equal to Rp by gamma f. This is the original equation, which is equation number 1, if you see, nothing but phi same as equation 1 which we have. Okay. So, we call this as design strength, sorry, design load, and this as design strength. So, though we have two components, which is the load acting on the structure and the strength which is depending on the material which is used to construct the structure, we do not use these values directly in the design. The reasons are very obvious, as we discussed in the last lecture, lot of variabilities, uncertainties. So, what we do? We modify these values as design load and design strength. The term design accounts for safety. Okay. So, the design is not because you are doing the design with the load. Okay. So, whatever load is encountered on the structure is different from the design load what you are using for designing the structure, they are different. Whatever strength of the material you have for the structure, for example yield strength, Young's modulus, ultimate, whatever may be the strength you have for the structure, the material, those values are not used directly in the design. You have got something called design strength, it means you are dividing that value. As far as strength is concerned, you are increasing the load as far as load is concerned. Okay, it is very important. Just to have a clue, if you look at concrete as a construction material for marine structures, gamma f, the load is 1.5 and gamma m, the safety factor for strength of the material, is 1.15, just for example. Okay. So, this number can vary depending upon what coat, what material, etc. This for example. Now, as we saw in the last lecture, you can classify the variabilities in the load as well as in the strength in different segments. Okay. So, they are all accounted together in one number which we call as gamma m, or in one factor which we call as gamma f. But many codes for design purposes split these values. Once they are split, they are called partial safety factors. The moment I say partial safety factor, then you can have partial safety factor for load, you can also have partial safety factor for material. Let us talk about loads. I should say gamma f is the safety factor for the load. I want to split this safety factor into different components which will associate for these uncertainties. I call them as gamma f1, gamma f2, gamma f3, they are all products. So, gamma f1 accounts for deviations of the load from the characteristic values. Gamma F2 accounts for combination of several loads and their, I should say, joint probability of occurrence. As we have been seeing in the last lectures, there are various loads like, for example, wind, wave, current, ice load, earthquake, etc. All of them do not act in a joint manner on the marine structure at all the time. So, what is that combination you account for? Okay. So, there is again a chance of error which one can encounter in assuming the combination of these forces. Now, gamma F2 accounts for that combination probability or the joint probability of occurrence of these forces together in a given structural system. Gamma F3 accounts for inaccuracy arise from mathematical modeling that is error between the computational load and the real load. There may be error, the real load can be x, but you are computing this as x1, x1 may be either higher than x or lower than x, that is not the material here, but there is a difference, x1 and x are not equal. So, this accounts for that inaccuracy which lands up from the mathematical modeling when you make to compute the loads. So, all of them put together accounts for a single safety factor in the load which we call as gamma F, which is multiplied with the applied load to give you the characteristic load or factored load or design load. Okay. Now, it is very unfortunate and very interesting fact to know that most of the international codes do not separate gamma F in pieces as F1, F2 and F3. They will not give you this, because all these to estimate independently in terms of its load is very difficult. So, therefore, many of the international codes do not give the breakup of gamma F value. For example, if I agree that gamma F value for concrete is 1.5, then I will not give the value of 1.5 equals to 1 of 0.75 of somewhere. I will not give these breakup associated with each one of them independently, because there is no guarantee that these values can be computed or is capable of computed accurately. Okay. So, you will always know only the joint safety factor which accounts for different deviations and variabilities in the load as well as in the strength. But as far as material strength is concerned, there is some intricacy available compared to the load, it is slightly better. Okay. We will talk about that when we do the design, how this is accounted for. Why I am explaining this? Because it is interesting that when you start working out these safety factors in terms of reliability analysis in the third unit, you would like to know what are those factors which will contribute for these gamma F and what would be the independent dependency of each one of them, because you can see here F1, F2 and F3 are independent of each other. one is talking about the deviation, one talks about the combination, other talks about the inaccuracy in mathematical model. They are independent actually. Okay. So, the cross dependency of each one of them is not there, but what would be the contribution of F1 on F, F2 on F, F3 on F is important. Okay. So, that would be interesting to know independently one of them or all of them, if you really want to know on what basis gamma f is computed based on reliability studies, which we will discuss in the third unit. Okay. So, we would like to know at that time this breakup of gamma f into F1, F2 and F3 will be important for us, that is why it is explained here, but the code is concerned, not only Indian code, many of the international codes do not explicitly tell you the independent individual values of these partial safety factors, that is why they are called as partial safety factor. I am interested only in the overall safety factor which is given in the code as is. Okay. Now, as far as material is concerned, there are various factors which are responsible for this gamma m. So, what are those factors which accounts for gamma m? One, variation in strength of the material. The moment I say strength of the material, I am talking about sigma yield value, Young's modulus, etc. Weakening of the material during erection process. There is a possibility here, I will talk about this quickly here. You have got a long plate in length and breadth, but the thickness of the plate is very thin plate. Can be a sheet basically, even if it is steel, if the length and breadth of the sheet is comparatively larger, for example 6 meters and 2 meters etc. However more you try to lift the sheet will start buckling or bending. Let us say you try to lift this plate by both the ends by a hook of a crane, the plate will start bending. So, obviously at the middle of the plate you are creating an high stressed section by erection process. It is nothing to do with the material deterioration at all, material is uniform, homogeneous, strength and properties are uniform across the cross section and across the breadth and length, there is no such hypothetical material, but you have created a difference and deterioration in the strength of the material because your erection process. Okay. This is very common in offshore structures and marine structures because welding is a process which will induce stress concentration on hot spots, which will create this kind of stress difference automatically in a given plane of any member or a material. That is what we put as weakening. This weakening has come not because of the manufacturing process, but because of a construction methodology or erection process. Construction inefficiency, I put them as errors. Let us take for example timber, which is one of the very common construction material for ship structures, let us say. Now timber has got very classical properties along the grain, in a given timber plane, across the grain. Okay, this is across the grain, this is along the grain. Okay. Now you are creating a plate or creating a column or a beam by joining different timber pieces or teak wood pieces together. If you misorient the alignment of these grains, you will land up in construction efficiency, because the strength along the grain is much lower than the strength across the grain. If you cross this, then you are creating an inefficiency in the stress distribution, which can also account for variability in gamma m. This is again a construction error or a fault. The second example could be the column may be of 12 meter long, should be of a single piece, but you do not have a 12 meter long piece manufactured, you have 6 meter long piece. You give this in 2 parts, but while erecting, the center of the top piece and the center of the bottom piece are shifted. So you are creating an eccentricity which will cause a moment at this joint. This is again a construction inefficiency, and so on so forth. These are all errors associated with the strength of the material, which has nothing to do with the load coming on the structure. Okay. So how gamma f is handled, gamma m is handled in international codes is a very interesting question. I can give you a clue here that it is better than, I should say, how gamma f is handled, okay, in the codes. We will discuss this in detail in the next lecture when we talk about the example, because I will take up an international code problem and try to solve that using that code. You will see that how gamma f m is handled in a different manner compared to that of gamma f in that code, and then you will see all these construction processes errors are all accounted automatically in estimating gamma m independently and explicitly. What I mean to say is, gamma m may have contribution from these factors independently, but like, or let us say unlike gamma f, explicitly these contributions are not available in the code, but certain codes give deliberately the contributions from these explicitly available in the code. There is a reason for this. By looking at these numbers of explicit values available, one can try to avoid these errors. Okay, these are all man-made errors actually. Remember, these errors are all created by nature except this. Okay. Whereas these are man-made errors, you could avoid inefficiency, you could avoid weakening of the structure, you could manufacture a material which will have a uniform strength, etc. Okay. Therefore, it is possible to evaluate this independently. So these values are explicitly available in the codes, whereas for gamma f, the partial safety factors independently and explicitly are not available in the codes. Okay. Having said this, we will talk about something called load effects. Now the loads and load effects are different. Loads are what is actually acting on the structure, effect is the consequence of the load acting on the structure, but it is not the response of the structure. Remember, load effects are not response of the structure, they are different. Response is associated with many factors. Can I name few factors? If you want to find the response of any given structural system for any given load which is known to me, what would be those factors based on which response can be computed? One is of course the material strength, 2 it would be the geometry, 3 it would be the support restraints, 4 it would be the modeling method. If you are looking for random vibration analysis, if you are looking for deterministic analysis, model method, or I should say analysis technique. then I should say arrangement of members. Etc. Geometry is nothing to do with the arrangement, this is dimensions of the members, etc. Okay. So, depending upon these factors, response is computed. Remember, none of these factors are directly affected by the load, okay, they are independent. So, I say load effect does not mean that it is response is different. Load effects are the consequence of the load coming on the structure, okay. To understand the load effects, I can categorize loads into 5 parts. Permanent load, I call them as P, live load, deformation load, environmental loads, and of course accident loads. Call this A, E, D, L. So, there are 5 categories of loads. So, let us quickly see each one of them briefly. If we talk about P, this includes time dependent loads, generally they can be determined with higher accuracy. They can be determined with higher accuracy. We already know what are the permanent loads coming on different example structures available in the literature. So, it is actually the mean value of the loads acting on the structure. You already know these values, you can take a mean value of this. If you really wanted to know what is a, let us say, the crane load coming on the deck of an offshore platform or a marine structure, you could see what are the varieties of cranes available in the market, what are the loads coming on the crane, you can take a mean value, you can find out that value as the crane load P on the deck. It means they are computed with higher accuracy, they can be computed easily with lesser errors. So, how does it mean that this effect will help me in estimating or minimizing the uncertainties? Now, I am looking at the effects caused by the loads, the effects are not the responses. Then what effects? The effects are what would be the probability of exceedance of this load independently. On the other hand, what is the probability that the permanent load coming on the marine structure can be exceeded? I want to know this. Since these loads can be computed with higher accuracy, since these loads are already based on some distribution technique, so the probability of exceedance of this load alone in a given marine structure is very low. Is that clear? Because they are already computed with higher accuracy. Is that clear? That is what we are looking at now. That is the effect what I am talking about. Live loads are associated with, this is the live load, loads arise from the nature, now therefore, the choice of characteristic value of the live load depends on the type of the structure what you are looking at. Talk about deformation loads. They are imposed deformations on the structures. Can you give me a very clear example of imposed deformation which can cause a load on the structure? An imposed deformation causes a load on the structure. There are many examples I can give you. Can you give me one? Imposed deformation which causes the load on the structure. Many examples. I am not going to explain them, just giving examples. If you have a very long beam, maybe simply supported, very long span beam, when such beams are constructed, you always give an upward camber to the beam when it is being constructed. When the shuttering is done for the beam, I am talking about long span beams, maybe the span exceeds 8 meters, 10 meters and so on, very long span beams. Even when the shuttering is done, an upward camber is being given, because this upward camber will settle down in due course when the concrete is being poured, because of the span effect settle down. Okay, it is an upward camber is given. So this imposes a deformation which is going to help in settling or avoiding excessive deformation of the member. On the other hand, if it have given the beam straight initially, then this delta would have been an added deformation due to the span effect alone. Okay, this is what we call as camber. This camber can be seen almost in all trusses. If you walk down to a workshop, you will see the bottom chord member, is never horizontal, it is always lifted slightly up. It is never horizontal. You can even visualize this from your naked eye, it is always lifted up, it is an upward camber given. And in structural analysis, you have heard about settlement of supports. When I have a beam whose support is settled with respect to the other one by an effect of delta, this imposes an additional moment, okay, 6E delta by L square, okay, that is an additional moment, and so on. So imposed deformation of the structure will also cause a load. The effect what you are talking about is this. Now for such loads, the characteristic values are prescribed to the maximum. Talk about environmental loads. They are, for example, ice loads, earthquake loads, etc. Their mean return period is being used to compute these loads. I already showed you an example. Now the question comes, what do you understand by mean return period? So mean return period is the number of years between the season to occur for its maximum amplitude. In simple terms, if the return period is 50 years, it is understood that the force is expected to reoccur, or I should say occur, only once in 50 years. That is called a return period. The same amplitude will reoccur after 50 years, that is called return period. Inverse of the return period, if you want to look at that, if you look at the inverse of the return period, will give you the probability that the extreme value of the load is exceeded in 1 year. That is called inverse of the return period. We will talk about this in the next lecture. So, we will elaborate this return period concept for wave and wind loads and their combination in the next lecture, and we will also talk about the accidental loads and the load effects on this. Once we understand this, we will see how the material strength can also be estimated or plays an important role in ultimate limit state or ultimate design mechanism or load principles in marine structures. Then we will finish this particular topic on ultimate load design, we will move further to the plastic design. Okay. So, we will meet the next class.